So hello everyone and welcome to this webinar series from Midas IT or Midas R&D Center India. So in this ongoing series of advanced numerical modeling techniques for tunnel modeling analysis, this is the second session. My name is Chinmoy and I will be your host for this session. So moving forward, the first session was on 3rd of April, which was about introduction to GTS and X features for tunnel engineering. Today, 6th April, we are going to cover the overview of TBM modeling methods in 2D. So, coming to the main agenda today, we'll start with just very simple introduction to numerical modeling and some TBM features. So, I'll give you a brief intro about TBMs and types of TBMs and their usage. Then I'll give you the overview of modeling approaches for TBM based tunneling. And then I'll show you in the GTS modeling features, I'll just tell you how it can be done in GTS. Then we'll go to the numerical model. And finally, towards the end, we'll have the GTS exclusive offer. So without any further delay, starting with the introduction session. So we'll start with the theory basically. Now, tunneling or tunnel construction methods can be divided into various types. I'm quite sure I have missed a few in these, but there are more too. So I'll just cover the most used ones. That is at first cut and cover tunnel. So it is basically for, let's say, subway stations or the tunnels which have almost negligible overburden. Then the DNB method, or it is the oldest method of tunneling. Then the TBM method, something that we will cover exclusively today and also in the upcoming sessions. Then the NATM method, which will be completely covered in the next session. Then finally the jacked box method. Now, giving the choice of which factor to take into account for tunneling, whether you need to follow DNB or you need to follow a TBM. So if we look at the cost versus benefit scenario in terms of site prep time, drilling and blasting tunnel can be erected or started with the least amount of time. But for TBMs, you need to dig down shafts and then the reinforcements need to be taken care of. So in that aspect, TBM takes a bit longer for erection. Then second is excavation rate. DNB is very much limited to how much mucking can be done and also the quality of blast and also the ventilation and other factors. And TBM, once it gets started, post 3 to 12 months, whatever is the shaft sinking time or the assembly time for the TBM, it is actually a rapid paced action. So it can go till 15 to 50 meters in a day, or it can even be lesser. It can also be higher, especially in terms of double shield TBMs. Now, coming to tunnel shapes, DNB is quite flexible in terms of what shape you want to give, but the fact is in DNB, it is nearly impossible to get the right shape at the first attempt. So normally what we see is either the final liner or the shotcrete thick enough that it has formed the actual contour of the excavation periphery, because it is very hard to get it correct in underground blasting, that the overbreaks or wedges not to form. They will form and they will fall down, which will create voids or a very uneven excavation surface. For TBM, the shape is exactly the shape of the shield or the cutter edge. So it is always going to be round. Coming to ground vibration. So we all know that with blasting, the vibrations will be high. So yes, in this aspect, DNB will actually have greater vibration. That is why the peak particle velocity is normally checked before blasting in any area. So you have firms like Orica or Dyno Nobel, which do these kind of studies, and they will come back to you and let you know about what kind of explosives to be used for blasting in any particular area. Because with the PPV issue, it is kind of critical for areas which have high population density or urban areas. TBMs have relatively low ground vibration, but it again depends if the TBM is working on what kind of soil or overburden it is. But if you compare both, TBM will be lower in terms of ground vibration. Next is the choice of method in terms of area localization. So drilling and blasting tunnel in populated area will be having several restrictions because of again the blasting based noise issues or vibration issues. But TBM can work unhindered in populated or unpopulated area, given the permits have been taken from the local authorities. Now, to the labor thing, with drilling and blasting, you will need blasting engineers, you will need drilling engineers, you will need tunnel engineers, you might need mining engineers. Okay, so and all apart from that, you will need technicians for each and every type of work. So yes, it needs skilled labor. And with TBM, a TBM machine normally comes with their own set of mechanics and technicians. But yes, in terms of access to skilled labor, both of them need the proper management of manpower to ensure that the project is delivered successfully. So with that being covered, we will start with TBM theory or TBM machines. So in the left picture, we can see a conventional TBM, the cutter head, which is followed by the bulkhead, then the conveyor belt that removes the muck away from the machine face, and then there is a working platform where the workers get the thing. I would say operators. The operators operate the machine and they plan on the further day ahead. Now, this entire machine is covered with a shield so that the soil doesn't cave in. So if you look for a trivia, TBMs are also called as mole. So in terms of types of TBM, based on the rotational cutter head, they are divided into two types, segment and gripper. So gripper is mostly for rocks, segment is for soft soils or normal soil rock mix. So in segment you have the either slurry type or the earth pressure balance type. The shield and mechanical also fall under the segment type. In gripper type, you will either have a beam type, that is open type, or a closed shield type. Now, the beam type cannot be used in soft ground. So apart from this, we'll just cover two of the TBMs, that is the slurry and the earth pressure balance TBM. If you are thinking about gripper TBMs, then one can take the reference of the Gotthard tunnel in Switzerland. That is the one of the deepest tunnels in the world, and that the tunneling has entirely been done using gripper tunnels. Sorry, gripper TBMs. So you can always go to the internet and look after it about the specifics of the project. Now coming to slurry TBMs. So slurry TBMs based on the methodology of pressurized slurry, which balances the groundwater and the soil pressure. So the cutter head is in contact with the soil for excavation, and then you have the slurry pressure that balances the machine, and then it is controlled by the bulkhead. So if we just break down into certain salient features of the slurry TBMs, the application is into granular soil and permeable ground where water inflow is expected. Since the soil is granular, so the permeability will be quite high. Then the important parts are as follows. The bulkhead, it maintains the face pressure here. Then the cutter head that is in direct contact with the soil, which has all the cutting tools embedded into it. The face support is done by slurry pressure. Then there is a protective shield to prevent the entire machine from the soil caving in from all sides. Then the thrust jacks, they provide the longitudinal thrusts to push the machine forward. Then there is a slurry treatment plant on the surface. The next type is earth pressure balance TBM. So although the purpose is same, but the application area is extremely different as compared to the slurry TBMs. The EPBs or earth pressure balance TBMs are very specifically applicable to soft or cohesive soils or soils which have extremely low permeability. So the working theory is basically that the machine turns the excavated material into a soil paste by using some binders or reagent, and that paste balances the pressure conditions at the face, avoiding uncontrolled inflow of water, or it can also execute rapid tunneling. Now, the components apart from the working theory are mostly similar. So here you have the cutter head that is again in contact with the face. It will also have jack thrusts. Then it will have the excavation chamber that is basically where the soil mixes with the paste. And then the bulkhead that transfer the thrust to the paste. So now we will see the tunnel modeling approaches. The first and the simplest one is wished in place tunnel lining. Wished in place is literally the word stands for the fact that you wish it in place. You can wish it to be existing anywhere. You just create a circular tunnel beam element, and then you excavate that tunnel, and then you check for the stresses and deformation around. The application area would be existing tunnel, or I would say preliminary studies or very initial studies where you are constrained by data and you just want to check the feasibility of the tunnel present in some part of the world. Pros are it is very simple. It can be erected in no time at all. Second, it requires extremely less number of inputs. So inputs are basically like just some soil properties and the depth of overburden that can also be varied here. And at least the benefit is that you can get a brief assessment of if this project is going to work or not. Cons, results are conservative. Results can also not be trusted because you are already working with the lowest amount of data. Next, line contraction method. So here we gather a bit of pace into the modeling part. So in this area, the application ranges for tunnels design impact assessment for existing infra. As you can see on the picture in left, we have a tunnel in there, and this is a building foundation where we have piles and a raft on top. Now here the liner forces are not of concern because we presume that liner is able to take up almost all the load exerted into it from the soil part. But again, the applicability is where we can have a debate about it because the whole concept of applying line contraction is literally the fact that you expect the soil to squeeze or the rock to squeeze. So it is a good assessment in squeezing conditions. Apart from that, if the ground is very stiff, this place or this particular theory holds no value. So in terms of pros, again, it's quite simple. So the number of inputs will be a bit more higher than what we get in the Western place. But here you can also apply the volume loss inputs in terms of, let's say, a percentage strain acting on the liner. And best part is the fact that you can actually this is the biggest concern, especially in urban areas, when you are inputting or you are, like executing a TBM tunnel where you have squeezing ground conditions. Because if the ground squeezes too much, there is a chance of the TBM getting stuck. And it has happened throughout the world that TBMs have gotten stuck. So this is a good assessment for taking a note of these squeezing ground conditions. Now cons, you it is actually we can say that the cons are that the forced heaving of the invert. That means since you are allowing a line contraction along the liner, you can expect a force heaving, which we will see when we'll take a look at the results. So second con is the ground contraction may be highly exaggerated. It might be possible too. And the third thing is the post-contraction liner forces are not representative. That essentially means that your forces may be way too high than what you can expect in the actual scenario. So the first two, Western place and line contraction, are, like Western places like the preliminary stage. This is like when you have some amount of data. Now, when you have most of the data, then you go for a full-blown TBM modeling like this. So when you go for a full TBM simulation, you carry out the simulation with phase pressure, pressure on the segments, pressure on the shield, the jack thrusts, okay, and also the contraction force acting due to the volume loss around the tunnel. Application areas being existing tunnel and feasibility or environmental impact assessment studies. Pros are you can simulate actual ground conditions. You can see the application of TBM forces, and the most important part is the phase by phase ground response result. Cons, it is actually time consuming. Second, it requires some degree of practice with either FEM or finite difference method or boundary element method or discrete element method. So there is a fine line between what we can design and what we can interpret, at the same time what is actually happening in the real time scenario. That is why we always need to have multiple methods to prove our own analogy is correct or not. So you have three different modeling approaches: line contraction method, a Western place, then the final full TBM simulation. So with the theory part being clear, I'll just show you a brief glimpse of the numerical model. We'll have two numerical models. First will be the Western place, which will directly just do in the software itself. Then the second one is a bit more complex than the Western place, but again, it's a quite simple one and can be erected in virtually no time. So this is our second model where we will introduce line contraction method. Now, the line contraction will be applied to the tunnel liner. So we have a tunnel in here around the overburden being around 20 to 25 meters, somewhere in the middle approximately. Then we have piles in here and a raft. So the piles depth is 18 meter, tunnel dia is 10 meter. The total length of the model is 165 meters, and the soil is divided into three layers. The topsoil is 2 meter thick, then the sand layer is bit permeable and it is around 13 meters thick. So the total depth of soil here is 15 meter. Then we come to mixed conditions where we have gravel plus highly weathered rock plus sand. So we just named it as mixed soil. For that, we took up a depth of 41 meters. Hence, the total model depth is around 56 meters. Length is around 165 meters. So we follow the hybrid mesh in here. The hybrid mesh kind of looks like this. You have quad elements in here. And you can see in the transition zones, we have triangular elements. So triangular elements provide the transition from a smaller quad element to a bigger quad element. So to ensure that the uniformity of the mesh remains same throughout the model. That is why both of the kind of elements are necessary. So this is the groundwater level, the blue line, or now I'm just picturing that here. So the groundwater is 2 meters below the surface. The tunnel liner. Finally, the loading conditions. So we will have at first gravity loading or the self weight. Then we'll have the foundation loads. So foundation loads will be applied to the nodes of the footing or the raft. So total is 900 kilonewton as shown in here. Then we are applied moment at the center. Now moment cannot be applied directly to a plane strain element. So we have to create a rigid link. So this is the master node. These are the slave nodes. Master, slave. So the moment is minus 125 kilonewton meters in the x direction. Then the strain is 0.1% as volume loss along the liner. So after that, the loading conditions are done. We just provide the boundary conditions, which are the roller supports on the side walls, and on the bottom we have the fixed supports. Then we have the construction stage wizard. So here we just activate and deactivate certain elements from time to time, which lead to our construction stage planning looking something like the video I'm playing right now on the right part of the screen. So at first we have the virgin ground, then we apply the foundation loads and the foundation elements, they are activated. Then the tunnel is excavated and the liner is erected. Then we apply the contraction load. Then we just deactivate the contraction load. That's it. So we'll have around 6 stages. 6 plus the initial will be 7 stages. Now coming to results, the ground deformations from the surface till the crown looks like this. Then the shear zone around the tunnel. Now if we look at the picture on the top right, you can see a large shear zone along the bottom of the tunnel. So while we check out the results towards the end, I'll request all of you to remember this particular picture because you'll find the exact correlation in there. But not to be worried, I'll explain that there too. Because remember, I said something about in the modeling approach that we will have unnecessary heaving on the bottom part or on the invert. So you can see the accumulation of the shear zones in here or the shear strains. The principal stress distribution around the tunnel. So these are for the ground elements. Then we come to the structural elements, the liner forces, bending moments. For the raft, the axial load, then the bending moment, then the axial load on the piles. In terms of output, you can export the 3D PDF report out of it, or you can export the entire thing into Excel. We'll have the inputs and all the load conditions defined along with the results. Or you can export all the images into Word file, or you can export the image into JPEG, PNG, or BMP format. So now we will go to the numerical modeling part. This is something I have reserved for the end, that is the exclusive offers for the participants of this webinar. So while I'm trying to open up the numerical model or the software, if you have any questions, please feel free to write them down. I'll try to answer them one by one. So I've got a few questions in here. So let me try to answer them. So I have a question that PPV value can be restricted while analyzing in software or Dillon blasting method. Please note that the PPV value is only for vibration analysis. So if you want to do a time history analysis with blast load applied, you can do that in here. Then I have other question that how to address variation in soil strata along the length of TBM in line model. So to address the variation in soil strata, either you can the model by the method of modeling different changes in 2D, or if your strata have extremely large variations in geomechanical properties, you need to go for a 3D model. So here we have the bedding plane wizard, where you can import your borehole data directly and apply the soil layers in there. That will be also covered in the upcoming sessions. So I have one more question, that how can we predict the probable failure zones? So the probable failure zones is the prediction is achieved from the numerical model. Okay. So I have a question that how to estimate the variation of ground deformation after blasting during tunnel excavation. Please note that for doing blasting based studies, That is a completely different science, so we are not going to cover that in detail in here. And especially for blasting based studies, India is a land of mining and we have very capable blasting engineers. So yes, we have in the country, we have the capability of people who have been doing these kind of blasting analysis and studies, and it is better to be left with them. That is a completely different science. So other questions like accounting for groundwater levels and seasonal variations possible. Yes, you can do a coupled analysis where you will have your water level rising and falling, or otherwise you can just go for static analysis where you model the water level, either like static water levels, that can be done too. So I think that's all the questions I'll answer for now. It's time to go back to the model. Okay, so in this part we will show you how it looks like. Okay, so this is how the software looks like. So I have left some questions unanswered, so I'll request you to wait till the end of the session. Okay, we'll have to cover the modeling part too. So please, if I have not answered your question, please bear with us. We will answer them towards the end of the session. Okay. So I'll go to at first define grid. Here I'll reduce the grid size to, let's say, 2 meters, and the number of grid units I'll bring it to 100. So what I'll do is I'll just create a random tunnel at the center. So I'll go to the circle option. I'll, let's say, create a circle like this with a diameter of 8 meters. So this will be my tunnel. You can work with the face option or without the face option. Both way it is possible to mesh the entire area. So I prefer not to work with the with faces unless I'm doing a 3D model. I normally tend to work with the wireframes or edges only. So in this part, I'll actually use the wireframe option. So my tunnel and my random ground. Oh, so I'll go to the rectangle option, left top, like this. So my ground and my tunnel. Now, when I mentioned at first that it is done with the least amount of data possible. So we'll assume the soil is linearly isotropic, and we'll just take some random uh, values for soil stiffness calculations, and we will use the Moore Coulomb method. So what I do next is I'll just hide the datum axis, and I'll use the intersect option to force the intersection of all the curves like this. Now, so my outer periphery of the ground and my tunnel geometry is complete. So next what I do is I'll go to mesh, we'll go to material, create isotropic. In terms of material database, we have a huge database. So you can use literally any kind of soil or rock model you want, provided it comes under the FEM theory. So we have Moore Coulomb, Hook and Brown, then strain softening, or we have CWFS, that is the cohesion weakening friction strengthening rock. or else we also have the generalized hook and brown, or you can have your own material properties too, where you can, if you can create your, you just applied the material model in Fortran. For soils, you can use more column. For more column, then you can use the uh, cam clay or soft soil creep. Then for excavations, you can use the modified more column or hardening soil. Then we have hardened drainage, and Rambia goes good for your for your hysteresis based soils. So the database is quite huge, but depending on your requirement, you can select what exactly you want to model. Okay, so I'll select here as more column. It is the easiest and the most widely used soil constitutive model. So I'll name it as just soil. So let's say we keep the properties intact if we do not change it. E model is 50,000, positive ratio 0.3, unit weight dry 20, nonlinear 21. Will not work with the permeability coefficient, so we'll skip that. So cohesion 30 kPa, friction angle 36 degrees. I'll press apply. Next, I just apply the liner. I'll click on structure. I'll go to database. In concrete, let's say I select M35. Press OK. So these are my properties for the concrete. I'll just put it as liner. Press OK. Then press close. Now I have created the geometry and the input materials. So now I have to create the element attributes. So I'll go to create 2D. First will be my soil. I'll press OK. Second will be my liner. That will be a 1D beam element. So I'll go to beam, click on section. The section type will be solid rectangle. Here you can see the stiffness constants. There will be no need to calculate anything on your own. The software calculates that for you. So the for the liner, let's say I pick up a 300 liner in here. So I put the height as 0.3, width 0.3. Press OK. These are my stiffness properties. I'll enter the name as liner. Oh, so I think I did a small mistake in the liner part. The material here should be elastic. I just need to click on the elastic part, then press OK. It will be changed here. So my liner properties, I'll press OK. So two inputs and then two element attributes. Now we'll go to the meshing part. So I'll go to 2D, click on auto area, select the inner area, or you can select both of them too. Click on mesh inner domain. But normally what I do is I'll do it separately, but I'll show you both of the processes. So let's say I select a size of 2. This is how your mesh is looking like. So let's say press apply. So if I go to the model part, you can see we have two mesh sets, tunnel and then the soil. So next what I do is I go to extract, edge, Extract the outer edge of the tunnel, name it as a liner. So if I go to the property drop-down option, click on liner, see this is how it looks like. Again, I will repeat myself that this model is a preliminary model with the least amount of data. So that's how you know like I can get a small model like this erected in virtually no time at all. So I just change the name by pressing F2 to tunnel. That's all. Now we'll just see the liner and then the element coordinates. So here we have to ensure that all of them point to the same direction. So I'll go to parameters, we'll go to change ceases, select all of them. Okay, align with one base element, this, apply. Okay, and then whatever is left, I'll just select them like this, and I'll just press to reverse normal. So now our meshing and geometry part is complete. I'll hide the coordinate systems. I'll go to the boundary conditions. I'll go to constraint, press auto, and name it as ground. I'll press OK. So this is how my ground looks like. So I have a question from engineer Kiran. If there is any structure close to the tunnel, how to include the stresses due to structural loads? Please be patient, sir. I'll come to the very next model in virtually no time. We'll be done with this. The second one will have the structures embedded into the model and also with the ground. So now I activate the self-weight option or the gravity. Name it as SW. Press OK. So as I have mentioned, virtually nothing in terms of inputs. So I'll just go to analysis. I'll go to analysis case, right click, add. So just for comparison purpose, we will do one linear static and one non-linear static. If we are correct, both of them should nearly be equivalent to each other. So we'll try to see that how closely the results are resembling for both of them. Now you can take into account the fact that if the liner is not thick enough, the model might diverge. So we will see how it looks like. The first will be linear static. In the output option, I activate the strain. I name it as, let's say, 1122. Nothing spectacular about it. I'll press add. So my first case is linear static, second is non-linear static. So I'll press strain. I name the second as 1123. Press OK. So now I'll just run the model. So I click on the Usain Bolt option and press OK. I need to save this one somewhere. Press save. So let's see. So both the analysis cases were solved. So what we do is we check the linear static first. We did a simple mistake. I forgot to deactivate the tunnel, so it's completely on me. I hope you excuse me for that. I'll just rerun the model again. Not to worry about it. So I have a question from Mr. Amit that is there is UBC 3D PLM constitutive modeling for liquefaction analysis. For liquefaction, we have NOR sand, PM for sand, and modified UBC sand. You can use any three of them. So I had one more question that the soil layer in the face and around TBM circumference are a bit disturbed. Yes, they will be. So how can we apply disturbed properties? Any correction needed in properties? So in those cases, there are multiple ways to model that. Either you can model that those particular zones as weak zones because they will be weak zones, right? The stiffness only increases some distance away from the excavation, not exactly at the periphery. So let's say in this particular model, this is my weak zone. So what I can do is I'll reduce the soil stiffness properties and assign a new property in there. Just allow me a moment. After checking the result of this particular model, I'll show you how to do that. So my linear static total displacement is around 510 mm. Okay. Non-linear static, it is around same 510 mm. Now, if I look for the beam element forces, so this is my actual load on the liner for non-linear static. So let's see for the static case. It is a bit low, but it's fine. It is less than the 10% margin, so I don't think that should be a big issue. Then the bending moments, I change it now to kilonewtons meter, 111 to 100 minus 126 in linear, in non-linear, 108 to minus 122. But the trend is same. So if any one of you who is new to modeling, remember your first model should be as easy as possible. There is no need to complicate anything. It should be as simple as this. But your results should follow the same trend patterns. And believe me, it is tougher to get similar trend patterns than the correction of results. So this is what you can call as a classic calibration problem. So at first, when you say we need to calibrate our model, this is how we calibrate it. By first of all, bring it down to the simplest of level and then slowly going up into a more complicated one. So if your results are matching in the simplest model, then that means your inputs are correct. So next, what we do is we'll go to a model where we apply the line contraction. So that will be a bit more complicated than this particular one. So I hope this small model was clear for all of you. Now, just to answer the question of that was a really nice question I got about from Mr. Vivek. So in terms of disturbed zone, you can use your empirical equations to calculate the length of the displacement zone. Otherwise, you need to shorten up the mesh a bit. Again, it's completely your prerogative how you want to follow that. So let's say I will reduce my material property. So my soil had this much, right? 50,000, 20, 30, and 36. So let's say I reduce the properties by 20%. Okay, so I'll just copy this one. I name it as soil DM. That means damaged. So I'll reduce the E modulus by 20% to 40,000. Non-linear 20% means 24. Friction angle 20% means 36 minus 7.2. Let's say I give it an even 29 degrees. So now once this has happened, that means your liner is going to take up extra loads. That also means that the soil around the liner can fail. So we will see if the model converges or not. So let's say I try to run the very same model. Now what I'll do is I'll go to mesh parameters. I'll select certain elements. Before that, I'll create a new plane strain property. Okay, I'll press it as DM. I'll press OK, and I'll select this zone around the periphery as my damaged zone. I'll press OK. So if I go to element attribute, your property is weak rock in here, or DM, or weak soil. If you go away from it, then it is just simple soil. So let's see what kind of results do we get. I'll just solve the nonlinear static scenario and we'll check for convergence. The model converged fine. So look for the displacement values, then the beam element forces. Then the strains or the shear zones. You can clearly see your extra deformed shear zone in here, right? Due to the weak soil layer. So this is how you can create or simulate your weak zone around the tunnel periphery. Now coming to the second part of the model. So this is it. So as I mentioned, this will be a bit more complicated than the first one for sure. So you can see my topsoil groundwater level at 2 meters depth, my piles. If I activate the property of the piles here, okay, piles, then my raft, my liner, pile tips, pile shaft, and my rigid link. So rigid link is where you apply the moment. I have sometimes seen people apply moments on plane strain or 3D elements directly. Please note that is not correct. You have to create a rigid link or a rigid body and then you apply the moment in there. So if I go to the material properties, the topsoil, I'll just change it to kilonewton meter. The topsoil has a E modulus of 22 MPa, unit weight 18, saturated 19, cohesion 4, friction angle 29, direct density angle 3, and tension cutoff is applied, at which tensile strength is 0. Then we come to mixed soil, the soil of 13-meter depth, the E modulus 30 MPa, cohesion 2, friction angle 30, direct density angle 5 degrees, tensile strength 0. Finally, the mixed rock condition. E modulus 120 MPa, dry unit weight 23.5, saturated 24, cohesion 50 kPa, friction angle 32 degrees, direct density angle 3 degrees, tensile strength 20 kPa. Then the pile shaft friction values. The pile shaft friction is taken to be constant along the length at around 355 kPa. Then for the pile tips, the pile tip has a maximum bearing capacity of 500 kilonewton. The liner here is a rectangular element of 600 thickness. And then the piles are 550 thick, 550 diameter each. And the raft has a thickness of or a height of 20 or 200 So here in the line contraction method, the construction stage analogy follows as this. At first, we'll have the virgin ground. Okay. Then we'll have the installation of foundation elements that are the piles and the rafts. So after the installation of that, we'll activate the rigid link, we'll apply the foundation load. Now, you do not build a building and a tunnel at the same time, right? That that should not be done. So what we do is, after that part is done, we use a reset stage. So what it does is exactly it resets the displacement to zero, so the ground becomes to the virgin state again, and then you start with the tunneling. So that is the brief idea that I wanted to convey to you. So I'll just show you directly how it looks like in here. First stage, only the ground elements. Second stage, the foundations. Third stage, the foundation loads and the moment and the rigid link too. The fourth is the reset stage, where we reset the ground deformations and strains to zero. So we assume whatever deformation has happened or had to be happened has happened. So from there we'll start as the zero level again. On the fifth stage, we excavate the tunnel, activate the liner. In the sixth stage, we activate the contraction. Finally, the long term, where we deactivate the contraction. So if I go to the results, for the first stage, the ground stresses kind of look like this. Total in x direction, total in y direction, then effective stress in x, effective y, then the pore pressure. In the second stage, we activate the foundation elements. So we'll just check for this stress redistribution now. Since they do not take any load right now, the stresses will nearly be equivalent to the existing ground conditions. Now in this part, that is the loading stage, you will see the change in the ground stress scenario. So we have applied the load in 10 increments. Okay, I'll change it to millimeters for the first increment. Then when the load is fully active, the deformation is now 8 Then the ground stress redistribution, major principle, minor principle, then the shear zone. We check for any plastic areas. So we have a little bit of plasticity around here on the edges. Then the forces on the beam elements, the actual load on the piles look like this, bending moments, then the shear force. Finally, we come to the tunnel excavation stage. Ground deformations. Now, in the start presentation, I told you that we will get unnecessary heaving due to the radial shape and applied contraction along the invert. So this is what you see in here. So if I just change the background to solid fill, if you can see maximum displacement is in here. So if I go to the value option, you can see max is around 15 mm in the bottom. So now you can say it is a very conservative assessment, because this is not usually the case that all the stress is going to be concentrated at the bottom or the invert only. But here we have forced that. That is why we are getting something like this. So if I go for the stresses, major principle, then the minor principle, and then if you want to check for the forces on the liner, if I go to beam element forces, so my forces on the liner, bending moments, again highest is in here in the invert part. So if you compare this with the contraction stage, you can see with the applied contraction, the value of bending moment has finally increased by around 10% margin. So if you just for comparison, I'll put it side by side. You can see the bending moment is 191 to minus 188, 178, and without the contraction it was 186 to 173, around let's say 5 kilonewton meters. Similarly, the axial loads, the shear force, and then the ground deformation. So if we look for the shear zone, I'll go to plane strain strains, Emax shear. So this is my shear zone. And the shear zone in the contraction stage is like this because we have deliberately applied the contraction load to the liner, which will again pass the load to the surrounding ground. And this is what we are going to get. So as per today's session, this was all I wanted to show you. So good luck and goodbye to all of you. And again, thank you very much for allowing us or giving us your precious time to showcase the features of GTS NX. So thank you very much. God bless you and goodbye.